Today I am going to explain about the topic channel equalization in wireless communication. This topic is important because it removes the channel distortion and inter-symbol interference. It improves signal quality and reduces transmission errors. Okay, we will see outline. First, the basics. In basics, basic definition and the simple explanation is going. And main body, it contains concept explanation, working process, and diagrams or flowcharts. In applications, where we will use this topic and the advantages and the limitations. And at last conclusion, we will see the 2 to 3 key takeaways and the final message. Okay, let's get started. What is channel equalization? Channel equalization is a technique used in wireless communication to remove distortion caused by the channel. It reduces inter-symbol interference so the received signal becomes clear and correct. It helps the receiver recover the original transmission signal even in noisy and multipath conditions. Okay, we will see the everyday examples. Everyday examples of the channel distortion. First one is mobile calls in cities. It will create echoes and fading from building reflections, causes voice distortion and dropped packets. And second example is Wi-Fi moving around the house. Reflections from walls and furniture create signal nulls and inconsistent throughput. And the third one is radio and TV reception. Multipath leads to blurred audio or video when multiple delayed copies arrive. Okay, why equalization is needed? Because the problem of the ISI. And this is the block diagram of the channel with ISI. And this is AK. The input symbols, the digital symbols are stored in the signal RAM and fed into the channel. And you will see here channel memory. Due to the multipath propagation, previous symbols remain in the channel and interfere with the current symbol. Delayed elements. These blocks represent time delays, showing how earlier symbols arrive late at the receiver. And these are the channel coefficients. Each delay signal is multiplied by a gain, representing the strength of each multiple path component. And this is the adaptive weight of the equalizer. And this sigma is the represents error calculation. And this is the delayed noise component. And this is the summation block. All delayed and scared signal components are added together, forming the ISI affected signal. And this is NK. This is the channel noise is added to the signal, further degrading signal quality. And this is ZK is the represent. The final received signal is the sum of the distorted signals and noise. And these are the points I have explained now. Okay, multipath propagation. We will see the picture of this multipath propagation. You will see a here transmitter, and this is the objects like home and the trees. These are the scatter, and here is the receiver. See now, the transmitter sends a signals that travel through the multiple paths to reach the receiver, and the one signal follows the direct line of sight path with minimum delay. See, this is the minimum delay where transmitter transmit the signals and receiver getting, and here first signal is transmitted from the transmitter and go through the scatter, and after it it is received by the receiver. See here, and this is the scatter also, the tree. The one signal follows the direct line of sight path with minimum delay, and the other signals get reflected by the objects like buildings and trees, causing delayed paths. These will cause the delays. For for remove this delay, we will use the channel equalization. All these delayed signals combine at the receiver and create inter-symbol interference. Because of this delay, it will cause ISI. Channel equalization is used to remove this distortion and recover the original signal. Okay, now we will see the equalizer. Equalization is the process to remove ISI and noise effects from the channel. And as I said, it is located at the receiver end of the channel. See, when we will transmit the data through the transmit filter and passes through the channel, and the other noise get added here, and it pass through the receive filter, and the input signal at last go through the equalizer. And this is the equation that x of f is equal to p of f into c of f dot h of f. It is an inverse filter placed at the front end of the receiver. See here, the transfer function of the equalizer is just inverse of the transfer function of the channel. Equalization is an iterative process of reducing the mean square error (MSE), the difference between desired response and output of the filter used in the equalizer. Okay, we will now see into the main body of this. These are the types of equalizers. First one is linear equalizer. Applied a fixed or linear filtering approximating the inverse channel response. Simple to implement but can amplify noise in deep fades. And the second one is decision feedback equalizer DFE. Use prior detected symbols to cancel post cursor ISI. Reduces noise enhancement relative to linear equalizers. And the third one is adaptive equalizer. This is continuously update coefficients, examples like LMS and RLS, to track time varying channels, critical for mobile scenarios. And we'll see through the first one is linear equalizer. What is linear equalizer? A linear equalizer uses a linear filter to reduce ISI by applying a suitable weights to received signal. This is how it works. The received signal passes through a linear filter. This is the linear filter. The filter coefficients are adjusted to minimize ISI. The output is a weighted sum of this output. See here. Output is a weighted sum of received samples. The key points are this is simple to implement. Like examples are zero forcing, MMSA, minimum mean square error. We don't go through depth here. We are just seeing the examples. Okay. This is a drawback. Noise amplification. This is the decision feedback equalizer. It contains feed forward filter and the feedback filter, and this is the symbol detector. We will see now points. Decision feedback equalizer uses a past detector symbols to cancel ISI instead of amplifying noise. We will see how it works. It has two parts as I said before. It contains a feed forward filter, and this handles current symbol. And another feedback filter is this uses a previous decisions. Previously detected symbols are fed back, and ISI caused by fast symbols is removed. The key points are better performance than linear equalizer. This is good one as compared to linear, and less noise enhancement and slightly more complex. And the third one is adaptive equalization. You will see how it will works. Adaptive equalizers are just filter tabs to minimize error between equalizer output and a reference, either a noun training sequence or decisions produced by the receiver. The first one is training. Send noun symbols, compute error and update coefficients. And the second one is decision directed mode. Use detected symbols as a reference to keep adapting when training needs. And the algorithms. LMS. Simple and stable. RLS. Faster convergence and at higher complexity. Here LMS means least mean square. And we will see the comparison between the linear equalizer and decision feedback equalizer. Here see there are three columns features and this is the linear equalizer and this is DFE mean decision feedback equalizer. This is the type, this is a linear equalizer and this comes under non-linear equalizer. The basic principle is using linear filtering to reduce ISI. Here we uses fast detector symbol to cancel ISI. Here feedback path, no feedback. Here feedback from the decision device. The noise amplification here is in linear equalizer high, here is low. And the error propagation is here not possible, here possible. And the complexity, it is simple and it is more simple and more complex. The performance of the linear equalizer is moderate and it is better than the linear equalizer. This is channel condition suitable for mild ISI, it is suitable for severe ISI. And implementation, it is easy to implement and comparatively it is difficult to implement. These are the example. Zero forcing, minimum mean square error. Here it is the decision feedback equalizer. Okay, we will see the applications of channel equalization in real world. Okay, it is used in mobile communication systems like 2G, 3G, 4G, 5G to reduce distortion and ISI. This is applied in Wi-Fi and wireless LANs for reliable high-speed data transmission. Used in satellite communication to combat long delay and multiple path effects. Applied in digital television and broadcasting systems for clear signal reception. Used in modems and data communication systems to improve bit error performance. This is the visualizing equalization. This is the before and this is the after. See here, before overlapping symbols, smeared amplitudes. Here smear means blurred. Okay, blurred amplitudes and noisy transitions. After separated from symbol fix, restored timings and lower bit error rate, enabling reliable decoding. See here, before, it is the before of, this is diagram of before the equalization. See here, overlapping symbols and high ISI causing smeared amplitudes. This is the after equalization. Clean separated symbols with low ISI and restored timing. See, here the amplitudes are the amplitude of peak of the amplitude is high. Here it is got mixed up. This visual highlights how equalization recovers symbols, boundaries, and reduce errors. The challenges and future directions. Low power constraints. Design equalizers that run. We have to design equalizers that run efficiently on battery powered IoT devices. And the second one is MIMO and massive MIMO. Joint equalization across many antennas increases complexity but boosts capacity. The ML driven equalizers. This will use neural models to predict channel behavior and adapt more robustly in complex environments. This and last one is integration with coding. Tighter coupling between equalization and error correcting codes improves overall reliability. And at last, we will come to the conclusion. The unsung hero. Equalization is the critical for overcoming multipath and ISI, enabling clear calls, smooth streaming, and reliable data links. From simple linear filters to adaptive and ML-based designs, equalizers evolve with network demands. And continued innovation will help the deliver low power, high capacity, and resilient wireless systems for 6G and beyond. And the key takeaway is the equalization turns messy radio channels into usable, high quality communication paths, foundational yet often invisible to user. Okay, we get to know how this topic is important, and I came through the simple definitions and real world examples and the types of equalization like linear, DFE, and adaptive equalizations, and we go through the applications and the limitations and the industrial uses and last with conclusion. Okay, thank you.